projects. In this video, we are going to explain about the project titled Grape Leaf Diseases Identification System using Convolutional Neural Networks and LoRa technology. The purpose of this project is to help grape producers by utilizing modern technologies. To monitor their grape crops, they employ little sensors that are online. These tools can provide information on the temperature and the presence of pests or diseases on grape leaves, among other things. Imagine having a small device in your garden that alerts you to need for watering or the presence of bugs that are eating your plants. This is similar to what these tools accomplish for growers of grapes. Powerful computer tools are also used in the project to analyze images of grape leaves and determine whether they are healthy or diseased. This assists farmers in identifying issues early and improving their crops. They utilize a specific form of low-power wireless technology called LoRa to make it all work, which is good for covering big regions. It resembles having a powerful Wi-Fi signal that can go great distances without consuming a lot of battery life. So, to put it simply, this project combines technology and smart devices to assist grape farmers in taking better care of their plants and producing better grapes. Objective: the goal of the project is to address the issues associated with picture transmission over low-power wide area networks (LPWAN), with a focus on the long-range protocol LoRa, which is infamous for its slow data rate. The goal is to effectively identify grape leaf diseases using low-resolution photos by combining LoRa technology with deep learning-based computer vision. Convolutional neural models (CNN) are tuned. LoRa settings are optimized, and on-site and simulation experiments are conducted as part of the project to show that picture transmission is feasible within the constraints of LoRa. Without the need for training data, the proposed framework effectively identifies diseases, and the application of explainable artificial intelligence (XAI) methodologies increases user confidence in the system by making CNN output judgments visible. Requirements. In the requirements, we have hardware requirements, in which we have operating system of Windows, processor of i5 and above, RAM of 8GB and above, hard disk of 25GB and above. Software requirements, in which we have Anaconda 3 and Visual Studio Community version. Flow of work. To implement this project, we have designed the following modules. The first module is importing the packages. In this module, we typically import the necessary Python libraries and packages required for the project. For a project involving image processing and CNN, common packages include NumPy for numerical operations and array handling, Matplotlib or Seaborn for data visualization and plotting, TensorFlow or PyTorch, deep learning frameworks for building and training CNN. Scikit-learn for data pre-processing and evaluation of the model. PIL, Python Imaging Library or OpenCV for image loading and basic pre-processing. Keras or Torch Vision, high-level libraries for building neural networks. Exploring the dataset, Grape Leaf dataset. In this module, we examine the dataset we are working with. This involves loading the dataset and performing exploratory data analysis (EDA) tasks such as checking the dataset structure, size and format, visualizing sample images of grape leaves, understanding the distribution of different classes healthy leaves versus diseased leaves, handling any missing data or anomalies in the dataset. Image processing. Image processing involves various techniques to prepare the images for training and improve the quality of the dataset. Common image processing tasks in this context include resizing and standardizing image dimensions, data augmentation to increase the diversity of the dataset, normalization to scale pixel values, pre-processing to remove noisy or artifacts in images. Data extraction into training and validation sets. In this module, we split dataset into two main parts, a training set and a validation set. These sets are essential for training and evaluating machine learning model. Training set. The data used to train the CNN model, it contains labeled images of grape leaves, including both healthy and diseased leaves. Validation set. A separate set of labeled images not used during training. It's used to assess the model's performance and fine-tune hyperparameters. Building the model, in which we have different algorithms. The first algorithm is CNN, Convolutional Neural Network. CNN is a fundamental deep learning architecture widely used for image classification tasks. CNN are composed of layers like convolutional layers, pooling layers, and fully connected layers. Convolutional layers are responsible for learning spatial hierarchies of features in the input images. Pooling layers downsample the feature maps, reducing computation and increasing the receptive field. Fully connected layers at the end make predictions based on the learned features. This is a generic term for a CNN architecture that we would design and customize for specific grape leaf disease identification tasks. It may consist of multiple convolutional layers, possibly followed by pooling layers and fully connected layers. The architecture design depends on the complexity of the task and the dataset. ResNet 50. ResNet, Residual Network, is a popular CNN architecture known for its deep network design. ResNet 50 specifically refers to a ResNet variant with 50 layers. It uses skip connections or residual blocks to mitigate the vanishing gradient problem, enabling training of very deep networks. ResNet 50 is pre-trained on large image datasets like ImageNet and can be fine-tuned for specific tasks. Using ResNet 50 as a base model can be advantageous for grape leaf disease identification tasks, as it provides a strong foundation for feature extraction due to its depth and pre-trained weights. MobileNet V2. MobileNet V2 is designed for mobile and embedded vision applications. It's known for its efficiency and low computational cost while maintaining good accuracy. MobileNet V2 uses depth-wise separable convolutions to reduce parameters and computations. It's suitable for tasks where resource constraints or real-time processing are important. MobileNet V2 is a good choice if we have limited computational resources or if we plan to deploy model on resource-constrained devices. DenseNet 121. DenseNet, Densely Connected Convolutional Network, is an architecture that emphasizes feature reuse and connectivity between layers. DenseNet 121 is a specific variant with 121 layers. It connects each layer to every other layer in a feed-forward fashion. DenseNets are known for their efficiency in terms of parameter usage and strong feature learning capabilities. DenseNet 121 could be a good choice if we want a model that leverages strong feature reuse and connectivity while managing parameter efficiency. Inception ResNet V2. Inception ResNet V2 is a hybrid architecture that combines elements of the Inception network and the ResNet. It uses Inception modules to capture multi-scale features and residual connections for gradient flow. Inception modules use multiple filter sizes to capture features at different scales. Inception ResNet V2 can be useful when we want to capture a wide range of features at different scales in grape leaf images. Training the model. This module involves using the selected convolutional neural network CNN architecture, that is ResNet 50, MobileNet V2, DenseNet 121, Inception ResNet V2 to train the model. The training process typically includes the following steps: pre-processing the training data, which may include resizing, data augmentation, and normalization; defining loss functions, optimizers, and evaluation metrics; feeding the pre-processed training data into the CNN model; iteratively updating the model's weights during training to minimize the loss function. The trained model learns to classify grape leaves into healthy and disease categories based on the features it has learned from the training dataset. Dumping the model. After training the model, it needs to be saved or dumped for later use without the need to retrain it every time. Model serialization techniques such as saving the model's architecture and learned weights are used to create a model file. Common formats for model dumping include TensorFlow's saved model format or the HDF5 format. The dumped model can be loaded and used for inference when a user uploads an image for analysis. Flash framework with SQLite for sign up and sign in. This module is responsible for creating a web-based user interface where users can sign up and sign in to the application. Flask is the lightweight Python web framework used to build web applications. SQLite is a lightweight relational database system often used for small to medium-sized web applications. Users can create accounts, sign up and log in, sign in to access the application's features. User authentication and authorization mechanisms are implemented to ensure secure access to the system's functionalities. User uploads the image for analysis. In this module, users interact with the application by uploading an image of a grape leaf for disease analysis. The uploaded image is processed by the application, typically involving the following steps. Image pre-processing, which include resizing and normalization to match the input requirements of the CNN model, using the pre-trained CNN model to make predictions on the uploaded image, displaying the results of the analysis to the user, indicating whether the grape leaf is healthy or diseased, and potentially providing additional information about the disease. The given image is processed using Keras image to array. When a user uploads an image for analysis, the uploaded image needs to be converted into a format that the CNN model can understand. Keras image to array is a common technique for this purpose. It involves converting the image into a numerical array where each pixel's color information is represented as numbers. This step prepares the image data for further processing and feeding it to the trained model. Trained model is used for predicting user data. Once the user uploaded and processed image is in the correct format, it is passed through the trained CNN model. The model then performs inference on the input image, making predictions about the health or disease status of the grape leaf. The predictions are based on the features learned during the model training phase. Predict with model for outcome. After passing the image through the model, the system obtains a prediction or outcome. This prediction typically includes information about whether the grape leaf is healthy or diseased and may include a confidence score or probability associated with the prediction. The model's output provides valuable information about the condition of the grape leaf. Displaying the final outcome. The final outcome, which is the prediction made by the model, is displayed to the user. This can be done through the web interface created using Flask or any other suitable user interface. The user can see the result of the grape leaf analysis, including whether it's healthy or diseased. Additional information about the disease, such as its severity or recommended actions, can also be displayed to the user. Execution. For the execution of the project, we need to open the code folder which contains the project source code file. This is the code folder. This is the static folder. This folder consists of files related to CSS, JavaScript and Bootstrap files. This is the templates folder. This folder contains all the HTML pages used in the project. It typically includes files like index.html, about.html, etc., which represent different pages of the website. This is app.py file. This .py file contains the information related to front-end logic. It includes code written in Python that handles server-side operations such as processing user requests, interacting with the database, and generating dynamic content to be rendered in the HTML templates. These are the model files which contain the algorithm information which can be loaded into the project code during runtime. This is notebook.ipynb file. This is a Jupyter notebook file which contains a combination of code, graphs and outputs all in one place. It allows users to write and execute code in individual cells, making it a popular choice for data science. This is signup.db file. This file is the database file used to store user information. First, we need to copy the path of the code folder from the address bar of the file explorer. I'm copying the path. Open the Anaconda prompt. Use the cd command followed by a space and then paste the copied path and hit enter. This command is used to change the current directory to the code folder's path. Compile the app.py file using the command python space app.py. I'm typing python space app.py and hit enter. This command will execute the Python script and perform a runtime check for any syntax error or logical issues. After running the app.py file, the Flask framework will host the application locally at the default address. This is the local address and port. Now copy this local link. I'm copying the link and paste this copied link into any web browser. I usually prefer Google Chrome and hit enter. The homepage of the project is displayed in the browser. This is the front end built using Flask framework. Now click on sign up button. If we are a new user, we need to register first, but I have already registered, so click on sign in. This is the login form. Enter the username and the password and click on login. This is the homepage of the project. So here we need to upload the grape leaf image, and then that image will be predicted as whether it is healthy or diseased. Now let us choose a file. Click on upload. So here we can see we got the prediction. This is the uploaded image. For the given input image, the diagnosis is grape black rot. So this leaf is diseased and this leaf is having a black rot. Now let us upload one more image. So this is the uploaded image, and for this image the diagnosis is grape black measles. So this grape leaf is having black measles. It means this leaf is having a disease. Now let us upload one more image. So this is the uploaded image. For the given input image, the diagnosis has grape healthy. So this leaf is diagnosed as grape healthy. Let us upload one more image. I'm uploading one more image. So this is the uploaded image, and for this image the diagnosis is grape Isaropios leaf spot. So this grape leaf is diseased from Isaropios leaf spot. So in this way, by uploading the grape leaf, we can predict whether the grape leaf is healthy or whether it is diseased. The conclusion of the project is the project's objective was to evaluate the CNN model's resistance to image degradation brought on by packet loss during LoRa-based transmission. Model robustness was given precedence over intricate structures or hyperparameter tuning. Findings showed that Resident 50, a CNN model, maintained its robustness to packet loss when the original image dimensions were preserved, and that data augmentation resulted to marginal accuracy gains. Downscaling increased noise but allowed for efficient image transmission over LoRa due to lower bandwidth requirements. Additionally, DenseNet proved to be more accurate during training and testing, which led to its selection for actual grape leaf disease detection using user-uploaded photos. This project demonstrates how CNN and DenseNet can handle scenarios with noisy data in the real world.
Thank you for watching video. For more projects, please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.